Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Shayan Majidy from Harvard, who will tell us about phantom codes, entangling logical qubits without physical operations. So Shayan is a Banting postdoc fellow at Harvard University, working with Misha Lukin and Michael Gulans. He did his PhD at University of Waterloo as a Vanier scholar under Raymond Laflamme and Nicole Junger-Halper. During his PhD, he co-wrote the textbook Building Quantum Computers as the lead author, which is published in Cambridge University Press. And his PhD work recognized with top honors, including the W.B. Pearson Medal, John Brody Memorial Award, and the IQC Achievement Award. So Shan, the floor is yours.
Thank you very much, and thank you for having me. It's a pleasure to chat with you guys. And feel free, please, to interrupt me at any point with any questions. I'm happy to discuss. So I was told the audience is fairly broad, and there's going to be some PhD students who are maybe earlier in their academic journey. So I'd like to start with a fairly broad introduction to quantum error correction. So around the world, people are trying to build quantum computers for different reasons. For example, maybe it's trying to solve a particular problem, doing a particular algorithm that we know quantum computers would be good at. And there's many famous examples here in cryptography or optimization. Or maybe more broadly, people are interested in simulating quantum systems, those that we can't efficiently simulate with classical computers. There's a lot of exciting transformative applications that lie in these cases, but they don't currently exist because error rates on hardware are just too high. So currently error rates are on the scale of 10 to the minus 2 to 10 to the minus 3. And while there's room to improve from hardware advances alone, there's no expectation that hardware advances will get us anywhere near the error rates necessary for large-scale quantum computing. And that's why in the early days of quantum computing, like in the mid to late 1990s, people thought quantum computing would just fundamentally be impossible. That was until the development of quantum error correction. Quantum error correction is the only known realistic method to sufficiently suppress errors for large-scale quantum computing. That's one take-home message I want you to have from my introduction. The second is that quantum error correction over the last few years has really shifted from theory to practice. And there's been a huge experimental surge. I made this slide not that long ago, but it's already starting to feel outdated. But here's some of my favorite experiments from the last few years. And while I don't have time to go through all of them, the point I want to make is that all the essential primitives of quantum error correction have now been demonstrated in the lab. And they've been done so with many different modalities: atoms, ions, superconducting systems, bosonic systems. And they've been done with many different codes. And the third point I want to make clear in my introduction is that the real frontier right now in quantum error correction is reducing the overhead. So here's a figure from a few years ago that estimates the cost of running different algorithms, such as factoring in quantum chemistry. And it maps here the number of physical qubits. So up here we have about tens to hundreds of millions of qubits. And here's we have runtimes on the order of years to centuries. And what we can see is that the current estimates, or the estimates at the time, were just prohibitively expensive. And so really a lot of the focus in the field the last few years has been reducing the overhead of quantum computing, reducing the number of physical qubits you need, reducing the runtime for the computation. And there's been advances. So here there's this famous paper by Craig Gidney on reducing the cost of factoring. And there's this recent atomic paper that made a lot of headlines. But again, we still have a long way to go to get to reasonable physical qubit counts and runtimes. So that's kind of the field where it's at now. But maybe, I've told some of you guys might be very new to quantum error correction. And to make sure you get something from this talk, I want to begin with a primer on just what is quantum error correction. And I think there's really just 5 things you need to know to understand quantum error correction. The first is that we store information non-locally across many different qubits. So if you take a single physical qubit, you can have different errors can occur. But instead, what we do is we take the information and we encode it across the correlations in many different qubits. And this many-body system of many different qubits together forms a single logical qubit. So before, a single Z error would cause a logical error on my physical qubit. On the logical qubit, I actually need 5 Z errors to occur and line up in a certain way. Similarly, a single X error would cause a logical error on my physical qubit. On my logical qubit, it would take 5 of these errors to cause a logical error. When you see codes like this, you're going to be defined with 3 parameters. N is the number of physical qubits. So here there's 25 little circles. Those are 25 physical qubits. Codes can have different numbers of logical qubits in them. So here this code block represents a single logical qubit. And D is the distance. It's the number of physical errors that need to occur to give you a logical error. And as I explained here, that's number is 5. The second thing you need to know is that unlike classical error correction, where we can keep measuring our system to see whether or not an error has occurred, if we just naively measure the state of our system, we're going to collapse our wave function and ruin our quantum computation. And so what we want to do is take these partial measurements called stabilizer measurement, which are going to allow us to infer whether or not an error has occurred without telling us anything about the state of our system. These are the stabilizer measurements that are types of parity check measurements. So you're comparing the relative state of, for example, these 4 qubits. The third is that the errors are discretized. So I mentioned in the early days of quantum computing, people had a lot of objections with it. And one of them was that computations seem analog. And if you know anything about analog computing, well, you'll know that actually analog computing classically is incredibly powerful. But the thing that really kills it is that error correction is not practically viable. And that's because the errors are continuous. So here, for example, what I've written is this is just an expression for some angle theta rotation around the x-axis. So some continuous error, because this theta can be anything. What it does is it creates a superposition of having your state with some amplitude and having an x error with some other amplitude. Peter Schroer's response to, so this is Rolf Landauer that wrote an article making this complaint. Peter Schroer's response was, yes, the computation is analog, but the errors are digital. And what this means is that when we actually go and do these stabilizer measurements, these partial measurements to extract whether or not an error has occurred, that active measurement actually collapses this superposition into either a state that's our initial wave function or our wave function with one of a discrete set of possible errors acting on it. Now that the error is discretized, we can then go and identify it and correct it. The fourth is that we need to effectively be able to correct errors faster than they're occurring. So there's this thing called the error threshold, this P error I have here. And if the error, there's this P error here is the physical error rate, and PTH is the threshold. If the error rate is below the threshold, then as I increase the distance of my code, my logical error rate will decrease. But if I'm above the threshold, increasing the distance of my code, essentially making my code bigger, is going to actually make things worse. So we want to be in a regime where we're below the threshold. So as we scale the distance of our codes operate better. And oops, not sure what happened there. Let's go. And then the last piece is around computing. And essentially, we don't just want to have memories. We just don't want to store quantum information with error correction. We want to actually compute with it. And we have to do so in a way that doesn't cause errors to spread. So here I have a picture of 2 code blocks. And I can connect the code blocks in different ways. I'm connecting them here with C0 gates. If I connect them in this way, a single X error will spread to 3 different X errors. And that's going to cause a logical error. So my computation is causing errors to spread. Alternatively, I could connect the 2 code blocks in the following fashion. And here, a single X error only spreads to one other X error in the code block. So errors don't grow. And so we have all these pieces together, and this is essentially the building blocks of quantum error correction. So feel free to stop me at any point if you would like any clarification on anything here. I'll continue. So at the core of quantum error correction, one of the major challenges we're facing with as a field is that physical qubits, so like a single atom or an ion, is effectively easy to control. And what I mean by that is you can shine some laser or some pulse and do some small angle rotation on the state of the qubit. Physically, that's very viable. Logically, small angle continuous rotations are actually incredibly hard to do. And it comes down to a fundamental tension that when we go and encode our qubits, we're trading controllability for protection. What we want to ensure is that what we're not doing is building a castle with no doors. We don't want to be in a situation where the decoherence isn't getting to our qubits, but neither are we. So what we want when we encode our qubits is we want fault-tolerant gates. We want addressable ones. So if we have some large code block with many different logical qubits, we want to be able to address the different logical qubits. We want to be able to address them in parallel. And we want to do this with as low as overhead as possible, because we know reducing the overhead, both in terms of the physical qubit count and the depth of the circuit, is what's going to limit quantum computing. So there's different approaches, and one that this work is really about is specializing codes for target algorithms or subroutines. I was recently at a conference and I was presenting this work at QEC 26, and there's this really nice poster I saw that I mentioned in the talk, and I thought I'd just mention here, that gives a very concrete example of this. You can imagine you take Shor's algorithm and you break it into its fundamental pieces. One of the fundamental pieces is an adder. You can then take the adder and you break it down again, and you see it consists of these Maj blocks. And so the Maj blocks can be written in different ways. This is one way to write it. What's nice about writing it this way is you can see that the Maj block only has 3 unique operations. There's this gate, and this gate. So if you can design a code that is very good at just these 3 gates, even if it's bad at doing other gates, then what you can do is reduce the overhead of the Maj block, make that very cheap, which in turn makes the adder very cheap, which in turn can make Shor's algorithm very cheap. And the idea here, you can play with this in different ways. One way is to just make your whole code block very efficient for a particular algorithm. You could also do this in modular ways, where you have multiple different codes that are specialized for different tasks. But however you do it, the idea here is to shift from like a quantum CPU perspective on computing to specialized devices like quantum ASIC or quantum ALU. And one of the reasons I think this idea is quite valuable, especially in the near term, is that we're not building quantum computers and we don't know what we're going to do with them. So unlike my laptop, I open my laptop and I don't know whether I'm going to check my email or I'm going to like browse the web or what I'm going to do. But if we're building a device now, we're building it for a particular purpose. We either want to like break RSA or we want to do a particular simulation. And many different architectures now allow us the ability to change our codes between experiments. So there seems to be a lot of runway in this specialization type of strategy. So the specialization, also in the literature, sometimes it's called co-design. There's a lot of open questions around it. One is, how do we actually take a code take an application or algorithm and optimize a code for it? So it's fine to say these are the gates we want, but how do we actually build a code that does those gates? A second question is around trade-offs. So even if you can make it so certain gates are as cheap as possible, what do you have to give up to make targeted gates as cheap as possible? So what are the trade-offs? And finally, how viable is it? So if you go and you're going to optimize a code to be very good at a particular application, you have to at least be better than the general purpose device. If I specialize to do a code for Shor's algorithm, but then some like general purpose, some like quantum CPU type architecture is much better at it, there's no point to specialize. So it also needs to be viable and actually needs to outperform general purpose schemes. And that's where this work comes in. Our focus here is minimizing the cost of in-block entangling gates. So within a code block, we want to specialize codes to make entangling gates within the code block as cheap as possible. And we're going to address these different questions as we go. But first, what is the minimum cost? How cheap can you possibly make a logical entangling gate? A precursor to that is the notion of doing logical entangling gates with permutations. So what I have here is the 422 code's logical operators written in a particular basis. It's a 2 logical qubit code, so that's why there's x1, x2, z1, and z2. What I can do is flip qubits 1 and 3. So I swap them and see what happens on the logical level. What we see is that x2 and z1 are unchanged, but x1 and z2 evolve. And the overall evolution is that of a controlled NOT gate. To say that differently, a physical permutation of qubits 1 and 3 has caused the logical controlled NOT gate between logical qubits 1 and 2. To draw this in a circuit, I'm going to use the 832 code. And here we have 3 different CNOT. I go to the physical level, and I can implement them with permutations, similar to the example I gave with the 422 code. I want to use the circuit to make the point that permutations are, interestingly, the unique set of operations that you can always pull through a gate without causing the complexity of the circuit to increase. So what I mean by that is I can, for example, pull a permutation through a CNOT, and I still have a CNOT. Or I can pull it through a Hadamard, and there's still a Hadamard. But if I try to pull a Hadamard through a CNOT, the number of Hadamards will spread. So the permutations don't increase the complexity of the circuit. What that means is I can always take the permutations, pull them to the beginning or end of the circuit, and absorb them into relabeling. On a physical level, you can imagine this picture where you have this CNOT circuit you want to do. You have these physical permutations where you're shuffling the qubits around. But instead of actually doing that shuffling, you can just absorb it into relabeling. So I want to step back and say, well, okay, make sure this actually is intuitive. Because you could say, well, on the physical level, you're not doing anything entangling. You're just doing physical permutations. How can something that's non-entangling on the physical level generate logical entanglement? So imagine a case where you have 6 qubits, and they're prepared in 3 bell pairs. And you ask the question, how entangled is subsystem A with subsystem B? Well, right now, they share 1 unit of entanglement. But if I swap these 2 qubits, they now share 3. And that's really the spirit of what's happening here. We're not generating new entanglement, but we're redistributing the existing entanglement that we already had to prepare. Like we already have to prepare our logical code words because we need the entanglement for protection. And we're effectively recycling or reusing or repurposing that entanglement to do a logical gate. Let's see what that looks like with a more involved circuit. So here, this is a random circuit that just illustrates all the different pieces that you might see. So we have some polys, we have some Cliffords, we have an interblock CNOT, we have some magic gate. So here, this is 2 832 code blocks. We go from the logical circuit to the physical circuit. So this is just translating each logical gate to its physical representation. And then we can recompile. And what happened is we take these 20 or so CNOTs, which would be done via these 20 or so permutations, and instead we absorb them into relabeling. And because we never actually have to do something physical on the hardware to implement the CNOTs, there's no overhead. And because there's nothing we have to do, then there's no infidelity from doing that operation. So no overhead, no infidelity, then again, at the level of the logical compilation, this must be the minimum cost. So we can define these codes. We can define a family of codes called phantom codes. They're codes that have 2 very strict restrictions on them. One is that they can do logical entangling gates between every ordered pair of logical qubits. This means every possible addressable CNOT in like every direction. So you can generate any CNOT circuit, for example, can be implemented solely via physical qubit permutations. So we don't even allow a single local Clifford. We can go through the literature to see if any codes exist that are phantom codes. And we find 2. One of the hypercube codes that were used in this Nature paper by the group that I'm currently in, where they showed a type of advantage from random circuit sampling with logical qubit. It's a very nice code, but its limitation is that it's distance 2, so it's just error detecting. And there's the Carmen code that was recently also published in Nature. The experiment was with trapped ions doing repeated rounds of quantum error correction. Here, the phantom property was very useful in reducing the overhead of the number of CNOTs you had to do, at least the number of them you had to do physically. But the limitation here is that it's only k equals 2. There's just 2 logical qubits, so there's only so many interesting CNOT circuits you can do with 2 qubits. So the open questions are, do other phantom codes exist? What are the practical limits of phantom codes? And do there exist regimes where they offer a practical advantage over the surface code as we scale the number of logical qubits? And then we want to do this under the real noise conditions we experience today in the lab to understand how viable this optimization type schemes are. And so why do we call them phantom? Well, entanglement is spooky action at a distance, and the C-naughts fully disappear. So spooky things that disappear are ghosts. And honestly, ghost code just didn't sound that good, so we called it a phantom code. Okay, I want to clarify what phantom codes are not before getting to our results. So they're not codes that have some permutation symmetries. So there's this very nice code called the tesseract code. And with permutations, it can do pairs of C-naughts together. But it's a very restricted set of C-naughts it can generate. And it can't, for example, do addressable C-naught, and definitely not the whole group of C-naughts. It's not logical polyframe tracking. So there's different ways to see this. I think the most natural is phantom codes integrate with transversal magic. So if I have a transversal magic gate, like I showed earlier in my slide, the permutation can still pull through without any increased complexity. They're not codes that only do gates in block. So for example, we prove in our paper that any logical C-naught circuit on B phantom code blocks can be implemented in just depth B. And it's not a scheme that we're suggesting to use one giant code block for the whole circuit. So part of our theorem too is that the number of physical qubits grows exponentially with the number of logical qubits. So to make the most of phantom codes, you would choose a k maybe in the range of like 4 to 6, choosing the number based off what naturally lines up with the circuit you want to do. So you find these like dense patches of logical qubits that interact a lot with via C0, and that's where you'd use the code block. Okay, so an overview of our results. So we construct many phantom codes. We have 140,000 instances plus some infinite families via 4 strategies, which I'll outline. We demonstrate, and by scalable here, I mean an advantage over the surface code as we increase the number of logical qubits under end-to-end realistic noisy simulations. We first prepare a resource state, so it's a GHZ-state, and then we do an algorithm, a toy model of a many-body simulation. And then some other results, which I don't have time to go into because the paper is quite long. It's about 70 pages. So I welcome you to read it if you're interested in any of these other things. We also study some of the limits of phantom codes, the other types of gates they can do, and practical tools that we had to develop for implementing non-QLDPC codes. So we construct our codes in 4 ways. First is a brute force enumeration. So we actually exhaustively create the database of all CSS codes up to 14 qubits. And then we go through the entirety of this database to find all phantom codes. We then use a SAT search method where we find the minimum n instances for different values of k and d up to n equals 21. So this allows us to push further, but it's not exhaustive anymore. And the limit here is in terms of going to high k and to high d at the same time. For that, we turn to analytic construction. So we have a quantum Reed-Muller family where we can get arbitrary k and d, but we run into a distance bound here. And so we come up with this other scheme for constructing phantom codes, which we call binarization and concatenation. And the distance grows quite nicely, but here it's limited to k equals 2. So this scheme can be seen as the extension of the carbon code to larger distances. So I'll go through a few of these. So with the exhaustive code enumeration, there's 2 challenges you have to address. One is you actually have to enumerate every single code. And the second is you want to make sure you haven't double counted. So we have to actually group them together if they're equivalent codes, which is a graph isomorphism problem, those who have thought about it from that perspective. Cross and Bandit have a very nice paper already doing this, where they get up to n equals 9 for all stabilizer codes. And their scheme is you begin with a trivial code, which is just n physical qubits side by side. You then add any stabilizer that's not currently in your code. What this does is it has the potential to increase d at the cost of lowering k. You then group the equivalent codes, and then you repeat. And you keep going like this until you generate all codes. I'll give you an example of how we did it. We optimized the scheme for CSS codes to be able to push further. So for example, we start with these 4 physical qubit code, and I'm just writing the parity check matrices in one logical basis for the operators, for those who prefer to see it like that. But if not, you can just follow what I'm saying. We then go and we add one stabilizer to the code, which gives us a 431 code. Because we're dealing with CSS codes, we have our first optimization, which is we only have to worry about the case where we have more X than Z stabilizers, because they're otherwise just related by a global Hadamard symmetry. And then what we do is we group the codes together by comparing their Tanner graphs. So for a 4 physical qubit code with 1 X check, there's only 4 unique Tanner graphs. And the way we make this problem much more efficient than just comparing the graphs directly is we map each graph to a canonical label, and then we compare the labels. We then repeat this process again. And because we're dealing with CSS codes, we have much nicer, simpler graphs to deal with. So it reduces the space of graphs. And we just continue along this way. Once we have all our graphs, we're going to use a SAT solver in a particular way to identify which codes are phantom. And I'll explain in the next slide how we do that. To give you a sense of scale, what I just walked you through was this light blue line here, going from n equals 4 through the k equals 4, 3, 2, 1 stage. You can start with different numbers of n. We do that up to n equals 14. You can see how quickly the number of codes are growing. About 10 to the 5 out of 10 to the 10 codes we find are phantom. And if we had stopped at the n equals 9 point, or cross and bandwidth stop, we would have had about 1/millionth of all codes that we have, albeit they did all stabilizer codes, and we just looked at the CSS codes. So we use the SAT-based tools in this work in 2 different ways. I guess briefly, what is a SAT solver? So you take a Boolean formula and you write it in this standard CNF form. So each of these are different variables, and these are logical or, nots, and ands. And what you do is once you have your expression, you ask the SAT solver to say whether the formula can be made true. And it either gives you a solution that makes it true, or it gives you a proof that it can't be true. What's really useful about this is we can use SAT solvers in this work to find codes with specific gates. So you can take a gate and write it in its binary symplectic representation. So this is telling you how it evolves logical operators. So you have here the logical operators for 3 qubits. And for a C0, it evolves the X1 and Z2, and it leaves the other logicals unchanged. What we do is we take this phantom condition and we encode it as a SAT problem. So we have different variables. So we have our logical operators, LX, LZ, parity check matrix, our symplectic inner product, and then PAB represents some permutation on the X or Z blocks. We then have a series of equations. The first one saying how the permutations act to give a C0 gate. And then the rest of the equations are saying the permutations essentially preserve our code space. And what we do is we can feed into the SAT solver a single variable, or we essentially take the permutation and make it a variable, and we give it a fixed H and L. So this is how we scan through the database of codes. We're giving it a bunch of H's and L's and asking it to see if there exists a permutation such that the code is phantom. Or we can use this for code discovery. And in that case, everything's a variable, and we just ask it to solve. So these are different ways which we can use these codes. Okay, I'm running short on time, so I'm going to skip over the analytic construction here. Let me just, I'm going to skip over this one as well. Yeah.
I think you have plenty of time, unless you had lots of things you wanted to say.
So I thought, I see it's at 36 minutes. I thought, I have 40 minutes? Is that right? Or am I?
I just mean that you time it like that so you can finish in 1 hour.
Okay. But I have an hour. Great. Okay.
Yeah.
No, if I have an hour, then I'll go through this. Great.
Yes,
Thank you.
Yeah.
Okay, so I'll take I can take a little bit more time, not too much time. We have some analytic constructions as well. And I think I should also say, right now, a lot of these tools I'm presenting them as tools used for phantom codes. They're interesting in that respect. But as I'll mention, all of these tools, and as we mentioned in our paper, can easily be repurposed for other types of gates you want to target, besides just C-naughts via permutations. So another strategy that's, again, fairly broad, is to begin with the quantum Reed-Muller code and then to fix certain stabilizers so that way you can, fix certain logical operators so that way you can create codes with targeted gate sets. Here we do it for phantom codes. So we start with an ordinary quantum Reed-Muller code. So for example, you can take the 1664 code. And then we can list off its stabilizers and logical operators from using monomials. Okay, if you haven't seen monomials before, then maybe you can just skip over this next minute. But effectively, what we do here is we have our degree 0 monomials, degree 1 monomials, or degree 2 monomials. In this case, degree 1 and higher are stabilizers, and between 2 to 1 are logical operators. And what we do is we gauge fix some of our logical operators to the plus state to allow us to have the freedom to map between any other logical operators via just permutations. And we can do this to convert these quantum Reed-Muller codes to phantom codes. And in a very nice geometric picture of you have these hypercubes, and then in a certain dimension you have, so in this case, you have a hypercube, and the squares of the faces are logical operators. And the permutations of the cube allow you to flip the faces around to do different logical gates. Our second analytic scheme is called binarization and concatenation. And the method is we start from a GF4 qudit code. So you haven't seen these before. It's not like GF4 codes in the sense where you take a classical GF4 code and make it a stabilizer code. It's actually a GF4 quantum code. So here we have the elements omega and omega squared as well. So here's a 312 code. So I'm going to just draw them as like little, each of these qudits is a little peanut. You then binarize the code, which effectively you're going to break the peanut in half. And you can map omega and omega squared and 1 and 0 to some binary elements. So omega becomes 1, 0, omega squared 0, 1, 1, 1, 1, and 0 becomes 0, 0. And so this 312 code, for example, becomes a 622 code. You then take this outer code and you concatenate it with a 422 code by taking these qubits and feeding them into this encoding circuit. And what you get in the 622 example is a 1224 code. And the 1023 example here, you get a 2026 code. So the input is a GF4 qudit code, and the output is a phantom code. Interestingly, the properties of the phantom code are in some degree inherited by the parent code. So the GF4 qudit code is self-dual, then you get logical Hadamard on the phantom code. If it's Hermitian self-dual, you get the logical CZ gate. Effectively, the intuition here is the 422 code, which is phantom, gives you the phantom property within a color. And then the 622 code that you got from the GF4 code gives you the phantom property across different colors. Or maybe I'll say it one other way, is that if you imagine this as like a concatenation scheme with different blocks, the last outer layer, the 422 code, on the physical level, you're doing permutations. And going through that block, the permutations map to C-naught gates. And what the outer code is doing is mapping physical C-naughts to other physical C-naughts, or to logical C-naughts. And all the codes we find, these are all phantom codes. So they all have C-naughts on all qubits in every wave of permutations. But they also happen to have a lot of other gates as well. So what we do is we take all of our phantom codes we find, and we feed them through a pipeline of finding other gates. So for example, you can find Clifford gates via automorphisms. So these are permutations and local Cliffords. How that works is you take the regular symplectic matrix for your stabilizers, and then you extend it to add this other term here. And what you do is you look for permutations on the columns of this matrix that leave the row space invariant and also are valid physical operations. So for example, flipping these 4 columns with these 4 columns leaves the span of the rows, like this row space here is invariant, these 2 rows. And so what you know is that it's a physical operation. And so the physical operation is, what takes 4 x's to 4 z's and 4 z's to 4 x's, that's 4 Hadamards. So we know the 4 Hadamards are a logical operation. We then go and check what logical operation they are, and they're a logical Hadamard followed by a swap. We'll also find magic gate. So we fix a certain level of the Clifford hierarchy, and we use a solver. That's an improved method of what was found in this work by Campbell and Howard. And effectively how this works is you're finding gates that are magic gates that on the physical level correspond to, for example, say you pick root t, there's some combination of combinations of root t on each qubit. So it could be like a t on the first qubit, a root t on the second, and a root t in the opposite direction on the next one, and identity on the next one, etc. And the third type of gate we find are fold gates. The way this works is we take our initial code, we extend it to a larger code. We bring in some ancillas and we use these C-naughts on every pair of qubits to create a larger code. And then we use a similar solver on this larger code. Then we map back to the original code. What this mapping does in this example here is the single qubit gates on the larger code are also logical operations on the smaller code, but they also correspond to two qubit gates. So this is how we get fold gates on the original code. The details of how we do each of these and like the pipeline for this is all detailed in the paper if you want to use any of these methods. And yeah. Okay, finally, we've gone through all this trouble to find phantom codes. Are they actually better than general purpose codes for a task that they're well suited for? You know, does specialization actually buy you something? So what we do here is we use a surface code baseline. So the surface code is kind of the king or the queen of codes for many reasons for computation. One is that the state prep is very easy. So we can just use bare ancillas and we do measurements of our stabilizers and we can prepare the code with very low overhead because the stabilizer, the surface code is a QLDPC code. Syndrome measurements are also very easy. You can do them in bare ancilla with hook-free error, with no hook errors. Decoder, we can use a close to optimal decoder with using matching. And we can benefit from very powerful tools like correlated decoding. So the surface code, has had 25 years of optimization, and it's really good it's been very strong for computation. We operate on a 6448 phantom code, and there's different challenges that we have to address to use this code. So this is in the spirit of the cost of specialization. One is it's not a QLDPC code, so we have to use a different strategy for state preparation. And here we're using a preselection factory. So what we do is we take one of these 6448 blocks, we then have a factory of 3 others, and we do permutations on each of them, and then use this pre-selection scheme, pre-selecting on these blocks. And here, to be conservative, we have 1 factory for every 2 blocks. We might have been able to even get away with maybe less than that, but okay, to be very conservative, we went with that. We use a very strict pre-selection to start. So with current error rates, our strictest pre-selection comes out to 24%. We also have to deal with different syndrome measurements. Again, because it's not QLDPC, we use a Steen-style quantum error correction, where we have to, again, logically prepare fault-tolerantly these ancillary blocks for X and Z error detection. And so it's not just bare ancillas. And we have to use a different decoder. So here we develop a spatial temporal sliding window MLE decoder, where you decode on a single window, commit to the change, and then slide the window around. So how do they perform? So the first task is GHZ-state preparation. So here we have one phantom code block and another phantom code block. There's some permutations in the block that we do, and these ones we can do for free for these C-naught gate. But the other C-naught gates, we actually have to pay the price for. So here, really what's happening is we're getting some savings in the very beginning, but then after that, we're paying the same price the surface code pays. So we're asking the question, how long does it take? How far do we scale before we lose? And so this plot here, we have the surface code at different distances, 5, 6, 7, and 8 here in gray. And then the phantom code using a strict preselection and a relaxed preselection. And what we find is actually we get some initial advantage as we expect, but the advantage actually persists even as we continue to grow the code blocks. We do this at current error rates and very near-term error rates. And if you fix the total qubit count, so for phantom codes, when you account for all of the factories and all of this Steen-style quantum error correction, and you stack all the costs together, You get about 4,600 qubits for 64 logical qubits. Comparing that to the surface code of a comparable number of qubits, that's distance 6, and we get about a 56 times improvement. If you want to match the distances, then we get a 4 times improvement, and we have half the number of qubits. We then go to a slightly more interesting task, which is many-body simulation. So here, we want to see a sustained advantage, again, as the qubit count grows. So here we have one Trotter step of an evolution where we do this 8-body Ising evolution. And we do it in a brickwork layout interspersed with X rotations. The way we do one of these blue blocks is we break it up. It's over 26448 blocks. So these C-naughts you can do via permutations, but the other ones you have to do them transversely with actual physical gates. And we do the same benchmarking. And what we find, again, for near term, for current on the left and near term on the right, for the current term, we get about 100x improvement if we match the qubit count. And if we allow surface code to have twice as many qubits as we do, we still get a 10x improvement. Okay, so where do we go from here? Really, the focus of this work was to explore specialization, so the methods, trade-offs, and viability. We raised some fundamental questions on limits. So to what extent can very large automorphism groups, so codes with lots of symmetries, like phantom codes, coexist with very high encoding rates and distances? What gates can and cannot be achieved with automorphisms? So for the first bullet, with phantom codes, we saw that you need an exponential, you need 2 to the k physical qubits for k logical qubits. Is that something fundamental to automorphism, codes with a lot of automorphisms? What if we reduce the number of gates we wanted? We didn't ask for all C-naughts, but we asked for some subset of them, or we asked for different gates. What's the cost of that in terms of logical qubits and distance? And then here the focus was just C-naught. We can ask the question, well, what if I want to get CZ gates or S gates or Hadamards? How do I do those in the most efficient and most cost-efficient way? Here we focused again on all in-block C-naught, but we could look at other gates and other circuit primitives. One example is the one I gave in the very beginning of the talk, but there could be others. The database we have, so here we have this huge database now of 10 billion codes. We can concatenate them in this quantum Lego style approach to build larger codes, go through them to find good magic state distillation schemes. People have asked for the database and we're trying to make it available, but it's on the order of terabytes. So we're still trying to figure out exactly how to make it available online so people can go through it. And we're currently labeling everything, so it's very nicely organized for everyone. So when it's finally out, you can search the gates you want, search the distance you want, and find it. So we're still working on that. The SAT methods we have, so SAT, using SAT for finding codes with targeted gates is a new idea. It's a new approach to using SAT in this space, but I think it can be easily adapted for other gates. And I alluded to this earlier, but this fully free approach where we want to pay absolutely nothing in terms of the operations we do for C-naughts is likely not optimal because of the number of physical qubits we have to give up. But where is the sweet spot? And some questions around the trade-offs, particularly for phantom codes, were looked at in this paper by Morris and Malls. And I think if you zoom out, you can imagine a space of quantum codes where you have codes that are very good for memory. So they have high encoding rates, high distance, and low stabilizer weight. And you have codes that are really easy for computation. And so phantom codes, while they're very easy for certain types of computation, they weren't as good for memories. And so we really want to see what are the trade-offs here if we allow some more flexibility. There's a large space to explore. That said, there's the questions around near-term feasibility of logical algorithms. So phantom codes are really optimized for densely entangling logical circuits. So Hamiltonian simulations seem one viable approach. Utilizing hardware with, say, around 30 or less qubits, I think you turn to the database. And a lot of people have asked me, my academic lab doesn't have the same number of physical qubits as, say, like Quera or like IBM. What do I do with 20 or 30 qubits if I want to do quantum error correction? Well, you need smaller codes, and we now have a full database of all the small codes. And finally, what is the role of these automorphism type gates in conjunction with other methods? So things like this, say like a partially phantom code, how would that interact with something like lattice surgery to reduce the overall overhead of an experiment? So thank you for listening. Hopefully I have enough time for questions. I want to thank my amazing collaborators, especially I think I always want to really acknowledge the contribution of the graduate students. Jin Ming, who's the lead author of this paper, did a ton of work with the numerics, and especially with the database, a lot of really impressive stuff there in the benchmarking. And see a lot of the insights around analytic constructions came from her. Andre did a ton of work with identifying the gates, creating our pipeline for gates. So I think, three very excellent graduate students, and you should, just wanted to give them their flowers. And also, as was mentioned, I wrote a book during my PhD. It reviews how different types of quantum hardware work. So, please buy me. Okay, so yeah, please, happy to take questions.
Yes, thank you very much for this very wonderful and illuminating talk. Yeah, right. I think we have like almost 10 minutes for questions, comments.
Awesome.
Yeah. So yeah, so anyone who wants to make a question or comment, please feel free to unmute yourself and ask it now. Not seeing anyone right now. Okay, so I'll start with something about so you basically categorize all of these codes. Is it like quite exhaustive?
So like this database of
Yeah.
Yeah, so in the database, we are categorizing by a few different things. So we have obviously the code parameters. So you want to know the N, K, and D. After that, you want to know the automorphism gates. So what gates can you do with local Cliffords and permutations? The stabilizer weights. So how low weight are they? And I believe that is it. So once we currently are running some numerics to finish all of that, but that should be available. Okay, once we figure out what's the best way to host it. So if you're watching this and you have a really good idea for how to host a terabyte of codes and like a searchable method, please email me. So we're like exploring different options for how to best do that. But yeah.
Let me see. Anyone is here for questions, comments? Not seeing anyone. I wanted to like get some idea of like so when you do this benchmarking for I guess you were saying that there was some particular applications where this would you feel like the advantages of these phantom codes would be most visible in some sense.
Yeah.
Yeah. Can you
Yeah,
say
so
a
I should
bit more?
start.
Yeah.
Yeah, for sure. So I should start by saying, I guess, so we've already seen them used in experiments twice now. So there was the Nature paper I mentioned by Misha Lukin's group on a while ago now using the hypercube codes, where this is using IQP circuit sampling. That's a task where you want to have, well, okay, so I'll say the two. And then the other one is this carbon code experiment where they did repeated rounds of quantum error correction. And for repeated rounds of quantum error correction, you're going to use a lot of CNOT gates within a code block. So I think what these examples show is not creating giant code blocks, so that as large of K as possible, but taking like a designed algorithm and trying to match the structure of the algorithm with the code block. So if you have like, say in the example we had of our Hamiltonian simulation, we picked this 8-body term because we are showing here like a 4 logical qubit code. But there in every block of like 4 qubits, there's a lot of CNOT gates between their immediate neighbors. So within these blocks of 4, there's a lot of CNOTs. And that's where like a phantom code would line up naturally. So I think the most obvious one, at least for me, is Hamiltonian simulation. So here, if you want to do like a 3-body or like a 2-body or a 4-body, whatever it is, Hamiltonian simulation, and you want to do some arbitrary angle, where you're going to do a single small angle rotation via whatever scheme you have. So say it's some kind of like, say it's like star, it's become popular recently, or it's like you have some other way to compile a small angle. You then inject your single small angle, but you want to now spread that over a many body term. And there's going to be a lot of CNOTs between neighboring qubits. And that's where like a phantom code would line up well with the structure of the code. So like some kind of Trotterized Hamiltonian simulation is the example that we had there.